Good morning, ladies and gentlemen. Welcome to our first video on anti-derivation, otherwise known as integration. Now, this here is very much related to derivation, and it's part of calculus. In fact, later on we'll do something called the fundamental theory of calculus. However, this takes it, I think, one step level of difficulty more difficult, because now we're doing the process that we become very good at, but backwards. So, if you take a look here, if we say capital F of x is a function where f dash of x is f of x. Note the little f. Don't get too caught up in the notation of big or little. It doesn't really make any difference. It's just a way to differentiate between the two. So what we can say is the derivative of big F is little f. And that's what we've been doing. If we find the derivative, then we go one way. But what we're looking at now is, well, what happens if we want to go from a function back to its original? What happens if we want to undo derivation or find the antiderivative? So here we would say that capital F of x is the antiderivative of f of x. So we're going backwards, and that process is called antiderivation. Alright, so just consider, ignore that for now, consider this on the left hand side. If we find, or if we know that f dash of x is 3x plus 2, then what is f of x? As in, if we've derived something and got this, where has that come from? Well, start with the x. We know that once we derive an x, we drop a power. There it's a power of 1, so it must have come from a power of 2. Alright? And that means that this 2, when deriving, so imagine heading back up this way. When heading back up this way, that 2 will drop out the front. But there's a 3 out the front. So 2 times what gets us to 3? Well, that's 3 on 2. Then here is plus 2. Really, you can think of it as an x to the power of 0 there, which must have come from an x to the power of 1, so it's just plus 2x. Terrible writing. 2x. Alright? The good news about this is you can always check using derivation. So if I told you now to take this and derive it, you would say, alright, well, the power comes down. 2 times 3 on 2 is 3. X to the 1 plus 2x derives to a constant of 2, and we're back at the starting point. So it's about trying to work our way backwards, thinking about, well, if this is the derivation, where has it come from? What do I go back up to? And this trick with dropping a power, whatever the power was down the bottom, is quite a common one. Alright, now let's consider what's over here. If I tell you f of x is 3 on 2x squared plus 2x plus 7, find f dash of x. So this is just ordinary derivation, going the normal way. 2 comes out the front, we get 3x plus 2 plus, well, nothing, because the 7 goes. Now note the difference between them. Here, we found the antiderivative and found that it was 3 on 2x squared plus 2x. Here, we found the derivative, and it was that 3x plus 2, the same thing as up here. Now what's weird about this is the 7. So, that 7 didn't appear here. If we found this, and found its, if we took the f dash of x and found its antiderivative, we didn't come up with a 7 here. Yet, when we have this function here, which does have a 7, we find its derivation, we end up here with no evidence of the 7. And this is because constants on the end, when we do a derivation, the constant on the end drops off. So, and this is very, very important, when you do an integration or find the antiderivative, there's nothing saying there couldn't be a constant on the end. So here, let's say we found this as our antiderivative of 3x plus 2. If we derive it, as in check our answer, that becomes 3x plus 2, the c disappears. Nothing. Okay, so what's very important when doing this is every time we find an antiderivation, we add c on the end to recognize that we don't know where it's come from. Exactly, we don't know if there was a constant on the end or what it was. And this is essentially recognizing that the relationship between these two is based on the slope of a line. And the slope of a line is independent of how far up and down the graph it is. So that C just translates the graph up and down. If we're going between slopes, then that doesn't matter where the C wouldn't make a difference to the slope. Alright, I've probably confused you too much. The important thing to remember is this cartoon. You lose marks if you don't add the C on the end when finding the antiderivative. Remember to add the C. Alright, so the notation for this is if you are finding the derivative of f of x with respect to x, so this is deriving with respect to x, that is integrating with respect to x, then we get this f dash x plus c on the end. Right? And it's called indefinite integration because it's not applied to any particular interval or any particular point. So it's a bit like we could derive a function at a point and find its slope. Here we can often integrate a function over a period, but right now we're just looking at indefinite integration. So just finding the antiderivative. Alright, now the cool thing about derivation is there's lots of rules, and you've seen almost all of these rules. These rules have power, addition, product, quotient, chain, e to the x, e to the f of x. We haven't actually done those two yet, but we will. Then sine, cos, tan, etc. Interestingly, in maths, any single function you can think of can be derived, but not every function can be integrated. And for this reason, integration is not always so easy, it can't always be done, and the course is only limited to a certain number or type of functions. And the idea is when you're integrating to break them down into these easier functions here. So these are the integral rules. Don't worry about this one just yet. But the rest, you should have some vague concept of where they should come from. For example, a constant, say that was the 2 before, has clearly come from a 2x, because when you derive 2x, you get back 2. But it could have come from 2x plus 7, because when you derive 2x plus 7, you still get back 2, hence the plus c on the end. That's what that's doing there. Alright, let's get into some practice questions. So these for practice here are integration of x cubed minus 2x squared plus 5 dx. Now the good news is when you integrate something that's broken up into parts, you can integrate it by parts. Not the technical word for it, but sure. X to the 3 minus the integral of 2x squared plus the integral of 5. And all of that, you can write little dx's on the end. So basically saying the integral of those three, you can apply the integral separately with separate dx values in there. Alright, so the question is now, well, where has x cubed come from? Well, x cubed has really come from an x to the 4. And when you were deriving that, the 4 would come out the front, but there's nothing out the front. Well, there's a 1 out the front. So that means there's a 1 on 4 here. Because as we derived, it would go back. 4 times a quarter is 1, x to the cubed. Minus. We keep that minus sign. Now this here has come from an x to the cubed. When that came down the front, it left us with a 2, so it must have been 2 on 3. Getting good at fractions is important here. Now the 5 must have come from a 5x. Now really, all of these little individual ones you could think of as plus c, plus c, plus c, because each time we do an integration we add a plus c on the end. However, there's no point writing c 3 times. It's an unknown. It just stands for an unknown constant. We only need to write it once, plus c. Alright, going on. Now here, once again, we're looking at this in parts. So I will write this as the integral of x to the minus 3 minus the integral of x to the half. And both of these are dx, dx. I have a bad habit of forgetting to write the dx's down there, but really you should. Alright, an integral of minus 3x has come from a minus 2, because when you drop the power down, it's there. So on the front, what's happened is the minus 2's come out, which means there must be 1 over minus 2, because minus 2 combines with the minus 2 to make a 1, and that gets us back to there. Second portion, if it's x to the half, it must have come from x to the minus a half. And x to the minus a half combines with something to get a positive out the front here. That negative there stays here. It wouldn't actually matter if you put the negative inside the derivation, but typically you throw the negative outside the front. And then this here, minus a half times what gets us positive 1? Well, it's minus 2 at the front. And so you can check by integration. If this came down, oh, apologies, I'm getting that very wrong. It's coming down, so it started at 3 on 2, and at the front it must be 2 on 3. The minus stays there, because yeah, it has to come down to a half, so it has to be above a half there, plus c. For the record, integration, I'm not a fan of. You're always thinking backwards, so the powers must always be going up. Note here that from minus 3 to minus 2, that's an up. From a half to 3 on 2, that's an up. And then dealing with the constants at the front. Alright, trig. So, do this by parts. Normally we think of the 2 on the front, sine x dx, minus the integral of cos x dx. Any constants you can throw out the front. That's why I've been throwing the minus 1s out the front here. So a 2 gets thrown out the front. Integral of sine x. Well, sine x must have come from a cos x. But cos x normally throws out a minus, so it must have come from a minus cos x. The 2 came in. Now, because you think about it, that there, once you derive it, would come out with minus sine. The minus would make that to make it positive, and the 2 stays to give you the 2 sine. Minus cos x. Well, minus cos x has come from a sine x. And sine x doesn't change sign. Plus c. Alright. 2 more. Now note, the way we approach this is different, as if we were differentiating. If we were differentiating, we'd think about this as looking like u squared, and then deriving it, we'd think about du. Here, we like these broken down into chunks. So we like the pluses and minuses in between. We're quite happy to do some algebra in order to get us to chunk world, where it's all nicely done in chunks, and we can do it little by little by little. Alright, so here we think about the squared. Now please, please don't write 9x squared plus 4x squared. Remember that anything squared is a pair of brackets, 3x plus 2 on x, bracket, bracket, 3x plus 2 on x. Integral dx. You can do any sort of algebraic manipulation between the integral and the dx. So now we have integral of bracket 9x squared plus 3 times 2x excuse me, 3 times 2 on x is just going to be 6. And that's going to happen twice, so 12. If you're not sure, 3x times 2 on x is 3 on 1 times 2 on x. 3x times 2 is 6x on x is just 6. And then at the end, we are going to have plus 4 on x squared dx. Alright, now by parts, 9x squared dx plus integral of 12 dx plus the integral of 4 on x squared dx. And instead of 4 on x squared, I'm going to write that as 4x to the minus 2 dx. Alright, this here must have come from an x to the 3. In order to get a 9 out the front, there must have been a 3 sitting there already. Because 3 times 3 gets us a 9, that drops the power x squared. So you might differentiating backwards. This here has come from a 12x. This here must have come from an x to the minus 1. X to the minus 1 will drop to minus 2, which means there must have been a minus 4 at the front. Because when the minus 1 came out, it combined with the minus 4 to make a positive 4, and then we're plus c. So that really looks weird with the space, but the answer is 3x cubed plus 12x minus 4x to the negative 1 plus c. And of course, if you took that and derived it, you'd end up back up there. Alright, this one here, once again we're looking in parts. This here is really half x to the half on the bottom. And we can write this in parts. So it's really x to the 2 over x to the half minus 2 over x to the half. You can split fractions up that way by taking the denominator and putting them in separate places. Alright, here we subtract powers. So integral of 2 minus a half is x to the 3 on 2 dx. That should all have been in brackets. Minus 2x to the minus a half, integral of dx. Right, this one will have come from an x to the 5 on 2, because that's one above, and because there's a 1 out the front, it must have been 2 on 5 to combine it to make 1. Then this here, minus. That would have come from an x to the half, and to get a 2 at the front, we must have had a 4, because half times 4 is 2, and the negative stays, plus c. Alright, so that's the last example. I'm sorry that went for so long, but remember the key principle here is break it down so you can look at it in chunks, then deal with each little bit in portions. Same with the trig. It takes practice and a lot of fun with fractions, but with practice it does get easier. Alright, thank you. I'll see you tomorrow in class.